double copy picture of strings in AdS.
Well, let me start by thanking the organizer to give me the possibility to be here with you today. I'm going to report on some progress about how to develop a double copy picture of strings in AdS. And this is some work that I made in the past in collaboration with these people, but mainly with Fernando and Doreli, who's a student in Oxford. In our last paper, it's kind of a mathematical paper, but I want to try to give you some perspective about that and why we think this is a good step towards developing this picture of strings in AdS. So I'll start by trying to motivate why it is interesting to study string amplitudes in AdS, and I'll give you the example of the AdS Virasoro-Shapiro amplitude, which is the starting point of how to generalize the building blocks of flat space string amplitudes to AdS. And then I will focus on this last paper, which was about how to develop a double copy picture in AdS, but in the full string theoretic setup. And I will conclude with some key takeaways and future directions. Also, please interrupt me at any point if this is not clear. Okay, so let's start by why it is interesting to study string amplitudes in AdS. And I will start very broadly by just stating that gauge and gravity theories have a crucial role in our understanding of physical phenomena. So very broadly, weak, strong, and electromagnetic forces are a manifestation of gauge theories, while we use gravity to describe the macroscopic evolution of the universe, as well as the structure of space-time. But we learned that we need to go beyond standard quantum field theory, which is the current way to talk to experiments, if you like, and we need to give up on traditional approaches to find a unified framework of gauge and gravity. And one such framework is string theory, that for us is going to be not a physical theory, but rather an elegant framework where you can treat simultaneously gauge and gravity. And the basic objects are one-dimensional objects, and the idea is that the different vibrational modes of the string will generate the spectrum. So for example, gauge bosons such as photons and gluons emerge as massless excitations of open strings, while the gravitons are the massless excitations of closed strings. Another very different perspective on gravity is given by the double copy perspective, which can be summarized schematically by saying that gravity can be seen as a certain squaring procedure of Young-Mills, which is a theory of gluons. And this is not manifest at all in the Lagrangian formulation that we are used to, but we need to move our focus on objects closely related to observable quantities. Before doing so, let me just state that both these perspectives are not only interesting as like frameworks, but they allow us to explore the perturbative structure of quantum field theories. So even if you don't believe in string theory as a physical theory, which is perfectly fine, you can think of it as a completion of your quantum field theory. And then the string has some length, and there will be a parameter called alpha prime. As you take it to 0, you're really recovering the point particle limit. So string theory can really teach you about the structure of quantum field theories as a space of theories. And that's our idea for today. So these observables are scattering amplitudes. They are interesting because, first of all, they describe the dynamics and interactions of particles or strings. And they can be used to test predictions for your theory, but also to explore conjectures. And one very important point is that through the study of scattering amplitudes, you can uncover structure and reveal symmetries that, again, may not be apparent from the Lagrangian or off-shell formulation. That's why they lie at the interface between particle physics, mathematics, string theory, and more. Scattering amplitudes exhibit surprising properties that encode deep lessons, again, about quantum field theories and also about gravity. And one of the most remarkable properties of amplitudes is this double copy. So let's state it. Double copy essentially is a way to compute amplitudes in one theory using amplitudes from simpler theory. So you compute an amplitude in a gravitational theory by recycling results from gauge theories, but they're usually way easier to compute. So that's the usual structure. The inputs are two single copy theories that can be different or the same theory, and they are glued together through this function, the kernel, which is just a function of the Mandelstam invariants, so the Lorentz invariant combinations of your momenta. And importantly, it is universal, so it does not depend on which gauge theories you are relying on. And this gives you back a double copy. So this kernel has a lot of interesting features. It has to cancel the spurious poles from the two theories, and it has to give you the missing poles in order to reconstruct the sensible gravitational theory. Yes?
What are alpha and beta in the formula?
They are the color orderings of the external particles. So you're doing planar amplitudes, there is a specific order of the external particles, and you sum over them. So this is really dependent on this, and you can interpret the KLT or double copy relation as a multiplicative map on the structure of QFTs. In this sense, it is useful to organize a web of different theories that may be very different from the first.
Sorry,
look at them.
for annotation, the kernel, does it depend on the polarization of the external states?
It just depends on S and T, like the Mandelstam variables. It's a very general function, and since it comes from string theory, it's just from monodromy properties of the string integrals.
So all the polarizations are in AL and the
Yes. Yeah, it does not depend.
Could you remind me, this double copy property is exact property or it's the kind of tree-level property?
The original statement is at tree level.
Mm-hmm.
At one loop there is evidence, it's not proven, but in string theory it should hold because it's really just a property of the integrals that enter the game of string amplitudes.
So you're saying for string amplitudes it holds at all loops?
I think up to one loop you can show it easily, and then to all loops I don't think it's been done. So the statement, the original statement is tree level any number of points. Then people worked out the one loop case, I would say, but not
But
all
so
loops.
it's not, for strings theory, it's not, because at one loop, at tree level is kind of semi-obvious from it. But
Yeah.
beyond tree level, I didn't think it's,
No, I don't think it's proven at all loops. No.
but is it expected to hold at all loops? Or?
I would say so. Like people question whether it is a way to span the set of gravitational theories like non-perturbatively, but it's an open area. So yeah.
Because if we want to use it as a computational tool
Yes.
at higher loops, then
No, I mean higher loops you can cut the loops and reduce the tree level, so you can still use the full computational power of the double copy at tree level.
Okay.
So that I meant as higher loop. Yeah. Reduced to tree level.
Mm-hmm.
And I just wanted to mention, even if this is not at all my area of expertise, that it's been also used in gravitational wave physics to reduce higher order corrections to gravitational interactions in GR, which would involve thousands of Feynman diagrams, but through like by mapping the problem to gauge theories computations, it's really way easier, and the number of diagrams is reduced drastically. But as I was saying, we would like to understand how similar structures emerge in curved backgrounds. So let me give you a very simple example. We have the amplitude of 4 gravitons at tree level, and this can be written as the square of 4 gluons through this computable kernel. It's just a function of S and T. It's quite easy. It's polynomial for field theory, and as we're going to see, it's going to be trigonometric for string theory. And the lesson to learn here is that the tree level for graviton scattering is completely described by gauge theory for gluon scattering, and you bypass the usual machinery of GR, which is quite powerful. And actually, this is true for any number of external states. So we can summarize this by saying that gravity is the square of Young-Mills, and we'll make this precise, of course.
Sorry, can I
Yes.
back to my question? If it's really true at all loops, yeah, what would it mean? Because Young-Mills is UV complete theory, so like,
Yes.
in principle we know all the amplitudes. So that would tell that there is a UV completion, it provides UV completion for gravity also?
I mean, I wouldn't say so.
Well, but then it cannot be true at all loops. Or
Well, you have a non-trivial function, the kernel, which adjusts things. So it's a computational tool in the sense that you input 2 amplitudes, and the kernel tells you how to do the gluing, such as you return a sensitive gravitational theory. So like missing poles and spurious zeros, everything is encapsulated by the kernel.
yeah, but the kernel you're saying is calculable just within field theory.
So you mean that the kernel could spoil UV completeness?
But it cannot, because
No,
it's
it
external.
cannot.
If it's a kernel, it's
But
You
just
can
an
calculate it in
external
gauge
parameter.
theory, right?
Then you
Yeah,
Then it looks
is,
like-
right.
Like I can just take 4D Einstein gravity
Yeah.
and say that I know everything about scattering amplitudes as Einstein gravity from
For
knowing
loops.
Young-Mills
Yeah,
scattering amplitude,
that's a good point, yeah, I agree.
which doesn't sound like a
Yeah,
plausible
that's not.
statement. So
But
there should
I don't know how it would fade to higher loops. Maybe it's not trivial.
Let me take your question, but in the other direction. So we know that Young-Mills theory can appear in a confined phase, in a conformal phase, in a Broughton-Glertz phase. And this we know by the external particles. Now, what does this show on the gravity side? How would you see that these different options, how would they
Like, for
manifest
instance, there is
themselves?
like one loop running in Young-Mills.
Yes.
What it corresponds to gravity?
Yeah.
It's really, yeah.
Because we know that there is lots of structure on the right-hand side, so
Yeah.
what does it impact on the left? Even at one loop, okay,
Right.
without
Yeah,
even
that's
V
it's really
completion.
one loop question. Yeah.
The answer is that I don't know. Like what we work on is three-level things, so not a lot of comments are not manifest. But I don't think the people worked out how to read the properties and in a systematic way. Even the one loop thing is worked out like in another setup, theoretical physics, and there is no progress beyond that.
But
at least in the
these amplitude guys, they have some evidence beyond 3 level, but that's for n equal
For supersymmetric.
Yeah.
but
n equal
it's,
4
Yes.
supergravity.
To
it's
4
not
and
for-
to H gravity.
Right,
Yeah.
it's not for.
yeah,
Yeah.
yes.
And indeed, people use that to show
Right,
actions of
yeah, there's
divergences
some-
into A.
Basically, there is a conjecture that
That's
somehow
right.
it holds,
That's right.
but it's
Then
not for
we-
gravity, right? Einstein gravity.
That's
probably.
why.
But even for supergravity,
Yeah.
then we know that this equivalence must break, right? Because n equals 4 super Young-Mills is finite,
Yeah.
Right.
but
When you do A, it will break very high to fall.
supergravity will break it soon.
Yeah.
Yeah, so I should have been more precise, but let's see this 3-level theory. And yeah, the one loop is supersymmetric.
In fact, maybe for higher loops, is it an equality or is an equality when you look at the maximal cut diagrams, which are better behaved because every internal line is cut?
I don't know many examples of higher loops. I mean, more of like in addition to the one loop supersymmetric.
For the into 4 into 8 relation, they have
Yeah.
to work out the higher loop.
Probably even beyond one loop. really.
Yeah,
some
definitely,
checks.
yeah.
I've just
some
seen the
many,
one loop
yeah.
case, honestly, so I don't know. Okay, so that's for 3-level again for the field theory statement, and the lesson to learn is that the dynamics of like the gravitons and the gluons is described by the same kinematical building blocks. So we're gonna rather look at building blocks today. And as I mentioned already, the origins of the double copy are actually in string theory, back to the 80s in this famous paper by Kawai, Lewellen, and Tai. So we're going to refer to the KLT relations in string theory and double copy perception in field theory. So since we will work in string theory, let me spend 1 minute in telling you what was different about a string amplitude with respect to a particle physics amplitude, because conceptually they are very different. And we are used in QFT to point particles interacting at the vertex. This is very different in string theory, where you have one-dimensional objects whose interactions are smooth processes, like joining and splitting of strings. So like, for example, if you have a closed string, it can propagate in space-time like this, or 2 strings can join and then give you a third one, like the 3-point case. And while point particle spans a 1D word line in space-time, the string will sweeps out this 2-dimensional wordsheet in space-time. And the key difference is that while interactions for point particles are localized at a point in space-time, in string theory interactions are embedded in the topology of the wordsheet. If you look at these 2 examples, locally they always look like a free propagating string, but just if you look for far away, they will describe globally an interaction. So in this sense, the wordsheet encodes the interactions. So when I'm going to talk about the 11 interaction, I'm going to show you a sphere, because that's really what matters. Like the topology of the wordsheet tells you which kind of interactions you're looking at. And the last difference is that in QFT you add terms to the free theory to describe interactions, while in string theory, at least in flat space, you just need the free wordsheet theory, for example, given by the use of Polyakov action. So you have a wordsheet metric, and then the space-time metric is the target space that embeds this wordsheet. And it's usually flat, but then we will try to extend this to curved space-times. So things scattering in flat space, you have a well-established perturbative setup. You have the wordsheet theory, and we can summarize the structure of amplitude in this way. So in the usual path integral formulation, you sum over the topologies of the worksheet as well as the metrics of the worksheet, and you have e to the minus s, which is the weight of the various options. And you will insert these vertex operators that correspond to your asymptotic states, and the amplitude is a sum over all this stuff. So you will expand, and we will have a 3-level contribution and higher loop contributions, but for today we're going to focus on 3-level string amplitudes that again are just spheres with some punctures that corresponds to these vertex operators mapped to finite position through a conformal transformation. And we have two parameters. One is GS, which is the string coupling constant. It's going to be tuned to 0 because you want to study weakly coupled strings. And alpha prime, which is the size of the string. And it was here. So it's proportional to the inverse of the tension of the string. And as you take it to 0, you study really the point particle limit. And as you vary it, you can study the very stringy behavior. So let's reformulate the double copy but for strings. That's the original picture in the KLT paper. And this tells us how to interpret closed string amplitudes as bilinears of open string amplitudes. Essentially, in this correlators picture, closed string amplitudes are correlators of vertex operators on the sphere, while open string amplitudes are correlators of vertex operator on the boundary of this disk. So the kernel tells us how to glue these two hemispheres, and that's essentially the full string theoretic prescription to do so at the level of worksheets. So another example now in string theory, the gluon and gravitons can be seen as like these massless excitations of open and closed strings. So if you do the same, now the four gluons are described by the Veneziano amplitude and the four gravitons by the Virasoro-Shapiro amplitude. And the kernel, the string theoretic kernel, is now a trigonometric function in SNT. But of course, as you take alpha prime to 0, we will recover the field theoretic one. And you will recover the picture of gravity as a square of Young-Mills. Now, what about curved spacetime? As you try to extend standard formulations of string amplitudes to general curved backgrounds, it's very difficult to do so, and in fact there is no technology to compute amplitudes even at 3 level, even if in principle there is a perturbative genus expansion. But in our favor we have different things. We can pick a very special background.
Well, there are cases in which you can do that, right?
Yeah, for like AdS3,
Yeah.
where the worksheet is known, but apart from that, no.
Does it work in AS3? Someone has proved it?
Yes, they did it and also checked that the same structure as ours holds. So yeah, exactly. So you specify two AdS factors in the background. It's a very special case because AdS is like a box. So you can think of this as a ball or a box, and it has a conformal boundary, meaning that it gives you a natural definition of what an asymptotic state is, which corresponds to the insertion of local operators on the boundary. So we're going to work with the CFT duality that allows us to write string scattering amplitudes in AdS through CFT correlators of the dual boundary theory, where we have the CFT techniques and a lot of computational power.
Sorry. So when you say string scattering
Yes.
amplitudes in AdS from CFT, isn't CFT correlators are string scattering amplitudes in
Yeah,
AdS?
and then you can compute them by computing CFT correlators. They are
Right.
the same thing.
It's just the same thing.
Yeah, but you do the CFT computation because
Right.
you know not to do quantum gravity. And moreover, you can study exact limits. So flat space is always going to be our starting point and source of inspiration. But also there are some limits in AdS where you can do exact computation and still teach you about the full theory, such as the high energy limits that we studied with Fernando, Tobias, Shinan, and Cleman. So we need additional tools to make progress for string scattering in AdS. And there are a lot of things that help us in making progress. We're going to mainly use the CFT correspondence and the exact limits, but we also have the worksheet intuition from flat space and number theory that helps us to find the right language to describe the structure, as I will try to motivate in a second. Okay, so to give you an example about how to make progress in this direction, I'm going to briefly summarize the progress in this AdS Virasoro-Shapiro program that was born 3 years ago with Fernando, Tobias, and João Silva. And the main object of study is the scattering of 4 gravitons at 3 level. So again, we have puncture Riemann spheres with 4 punctures. And the example is AdS5 crosses 5, where alpha prime corrections are challenging to compute, even in the presence of a maximally supersymmetric dual CFT, which for those of you who like CFTs is for d n equals 4 super Yang-Mills. That's a central topic even for integrability communities. So the Virasoro-Shapiro amplitude is one of the earliest and more significant results in string theory. It was actually a result even before it was understood as a result for strings. And actually, Veneziano guessed it first for open strings, but now we know that for closed strings or gravitons, it takes this remarkable form as the ratio of gamma functions. And it was not known at the time, but now we know that this can be described by this integral, which is the worksheet integral that I was mentioning before. So here, S and T are the Mandelstam invariants, while Z, you can think of Z as the cross ratio of this sphere. So like some conformal invariant combination of the locations of the punctures. And what about AdS? In AdS CFT, we're going to focus again on a specific background, and then we will extend to general backgrounds. Start with AdS5 cross S5. This is the correlator of 4 stress tensor multiplets. The stress tensor is going to be dual to the graviton living in AdS, essentially. And this is true to leading order in the large central charge expansion of the holography. So one significant property of this amplitude, which is maybe less appreciated, is this alternative representation. This seems like a mathematical fact, but it's quite deep. If you look at this representation, it's exactly the same as this, but you can notice that there are some very special numbers appearing here that are called zeta values. That are the Riemann zeta function at integer values. It's a very number theoretical structure, but the lesson to learn here is that only the zeta values at odd integers appear in flat space, and they are the ones which are single valued, in a sense that I will try to explain later.
These are unique, like the polylogs, right?
Yes. So you can think of the zeta as the polylog at 1, and you do the single at 1. So this is an evidence in flat space, even if it's not understood physically. If you study 3 levels string up to the flat space, they have this single valueness emerging everywhere. Even if you look back at this worksheet representation, the integrand is manifestly single valued as you move around the puncture. And that's kind of related to this single valueness of special numbers appearing here. So the idea was, what if we assume that this is also the case for the AdS corrections? And this was really the turning point of this program.
So sorry.
Yes.
This can be thought of as sort of string theory, also respecting some kind of maximal transcendentality expansion or something.
Yeah, so in flat space, yes, and in AdS it seems to be the case in AdS5 as well. But it's, yeah, I don't think we understand it, like where it comes from.
So by saying
Because the gamma functions are increasing in powers in each term of expansion. This is what happens in superconformal field theories sometimes, for example.
But this is alpha prime expansion, no?
Yeah, but each term in the series of n, you see, comes with a higher power of transcendentality, in the sense that this is a.
But this transcendentality business, that's in the loop expansion usually. Here, somehow you're saying
Yeah,
there is also some maximum
yeah,
transcendentality also in alpha prime.
Yeah.
Yeah.
But sometimes this transcendentality also appears, for example, expansion of epsilon b in the dimensional organization
from
parameter.
integrational massive
Yeah.
string models.
Yeah, it seems to be there also in AdS,
But it's different from the one, what Sergei is saying is different from the expansion in which it appears in gauge theories.
Right?
yeah.
Yeah. A different organization of
Yes, definitely. Yes, thanks. So the progress was made based on 3 key points. The structure of poles of the amplitude, which is a bit different from flat space. Now you have higher order poles. This assumption about the low energy expansion. So low energy means alpha prime to 0. So the supergravity limit to your point particle limit, and then a tower of stringy corrections. They assume that the unknown coefficients are single valued zetas as in flat space. And then you have intuition from the worksheet. So the most basic idea was, let's keep the worksheet integrand as it is in flat space and insert another function, which is still single valued, but we want to pick the relevant one, such as in low energy we still have the same special numbers. Yes?
I'm just wondering, so the zeta function, it's single valued everywhere. So why are the odd ones referred to as single valued?
Yes, I agree with that. It's just a way to say that if you see the zeta value as the polylog at 1, it's a special function. there is a single-valued map which kills the polylogs at even integers and preserves the one at odd integers.
Okay.
So in this sense, we call it single-valued zeta value.
Okay.
So yeah, let me be a bit more precise. Just 2 slides about what is the right language of functions. And these are the functions that are going to be put here. So it's called multiple polylogarithm, and is a function L labeled by a word W. And this word is made by letters in some alphabet. For us, it's going to be 0 and 1. And the length of the word is called weight. This is recursively defined by these differential equations. And in some limits, you recover very standard functions. For example, the polylog with a string of 0 is just the power of a standard log. If you take a string of 0 and the 1 is just proportional to the classical polylog called Lien. And then we have more complicated things. So as you can see, a key point is that they are multi-valued on the complex plane, so you have branch cut at 0 and 1, but we like single-valued things, for what I was saying. So what we can do is consider linear combinations of polylogs such that all the branch cuts cancel, and there is a precise way to do so, this single-valued map. And for example, for this case of the log of z, which is multi-valued, you can add a log of z bar and it returns something which is single-valued. But you can do this at any weight, and any combination is being classified by Francis Brown, who's working in number theory. And in this sense, multiple zeta values can be defined as polylogs at 1. So in this sense, the single-valued map really acts on the polylog, but we use a little abuse of notation and say the single-valued zeta in this context. So this led to this proposal for the structure of the string amplitude in AdS. So originally it was AdS 5 crosses 5. And the proposal is the following. First point, we think of the AdS curvature as an expansion around flat space. So perturbatively, we start with A0, which is the Virasoro-Shapiro flat space, and then you have this perturbative parameter, which is alpha prime over r squared. R is the radius of AdS. So the AK is the kth order AdS correction. And the proposal is that at each order, it still has a representation in terms of a genus 0 worship integral, as in flat space at 3 level, but now you have extra insertions of polylogs. Of course, to be precise, you have to pick the right weight and the right structure in order to match the poles. But yeah, this is a proposal, and it, like if you take some input from integrability and other communities, which tells you like essentially which operators are exchanged, you are able with this proposal to compute in principle each AdS correction. And it seems to be working because it matches all the known results from localization and integrability. And even more interestingly, turned out that the same structure holds in other backgrounds as well. So there has been progress in AdS 5 crosses 5, AdS 3 crosses 3, AdS 4 cross CP3, and even for open strings in other backgrounds. And the structure is always the same. So it seems there is some universality which mirrors what happens in flat space. There is this universality across space-time dimensions in flat space as well. So this is also something very promising.
The problem is this capital S and T, what are the subconformal ratios?
They are still the Mandelstam-like variables, but it's a Borel transform of them. So it's a bit technical. But so usually in the SFT, you start from position space,
right.
You do a Mellin transform.
So it's a Mellin transform?
No, it's a Borel transform,
okay.
Which is a further step.
Okay.
It is the one that you need to do to recover flat space. So if when R is infinity, the Borel transform of the Mellin amplitude is the Virasoro-Shapiro amplitude. Mm-hmm. Then we conjecture that this also gives you the AdS curvature corrections.
Mm-hmm.
So
so there is no straightforward translation into coordinate space.
No, you have to do 2 transformations back.
But
this is also not.
Not all of these are evidently critical string series. So does this input enter anywhere? I see AdS 5 crosses 5, okay.
Yeah.
I guess you have to think also of the backgrounds, the Schwartz, etc.
Yeah.
But the others don't look like critical. Is this an input? Does it sit somewhere in the calculation?
Probably it's invisible at tree level.
Yeah.
We'll start showing up at the higher genus.
So you don't see the anomaly.
Yeah, for example, for the second one, there could be some internal to like a T4 K3.
So it's not complete.
Just not visible from the tree amplitudes.
But also in
The
the
geometry
ADS
for volumes
background,
brains usually embedded in the
the ADS background has a Ramon background. Which, so how do you do calculations inside
The
that?
last one.
You don't know how to do computation.
So
It's like
where does this amplitude, this expansion come from?
It's a bootstrap procedure from the CFT.
So in the case of ADS3, you can do it with no
Yes.
Ramon, and it works. Is the only case in which you're right. You're totally right. In the case of ADS3, it's the only one in which you can write down the worship thing and see
But
it.
for ADS5, so what does it mean, bootstrap in this case? Bootstrap
This is
in
the
what?
so you kind of you conjecture this kind of expansion.
Mhm.
You know what kind of functions define as W3 and W6, and you use integrability input to fix those functions.
So the specific coefficients appearing in each curvature corrections are unfixed,
Mhm.
but they can be mapped to like the residues of the poles of the amplitude. And this is being computed by integrability or localization. So
Mhm.
once you have that input, the answer is completely fixed. But actually, like single valuedness by itself is able to fix completely the first curvature correction. You don't need any help there. For the second one, you need help from integrability and presumably also for the higher ones.
So is any, in this formula, is anything related to these old calculations of Polchinski and I don't remember whom on scattering amplitudes in ADS?
The hybrid form of it?
Within the
No, not the hybrid formula.
in the flat space, the
Yeah.
limit.
Yes, where you have
Mm.
basically the intuition that when you have two very high energy
Yes.
particles,
Yeah.
when they scatter, they see flat space because.
Yeah.
We studied that. I will go back to that.
Mhm.
That can be used like in addition to integrability. It's like
Mhm.
you can do this in high energy. The answer is completely fixed, and this helps fixing some confusion spots.
Mhm.
Yeah, this is finite SNT. Then you can do limits and do exact computations for sure. And I will go back to that.
And this expansion is the same for the bosonic strings, superstrings, type 1, type 2.
It seems to be the same structure in these backgrounds, which is type 2 and type 2A, type 2B. It's still an open question, like it's to,
No, because it assumes integrability, right? So
Yeah.
that's-
I meant integrability for in the cases
Well,
where you
integrability
can use it.
fixes those the coefficient in the structure.
Right.
Yes.
But I think Mary want to claim the structure is more general.
Yes, that's what it seems to be the case. Then integrability is a way to fix the coefficients in each piece, but we still don't understand like what's this universality of structure. This is
But when you say
right.
it seems to be the case, what is the evidence
like
for that?
other people did the same computations for other particles in these backgrounds with this structure, like without fixing the coefficients, and then they can get like the CFT data that agrees with a computation that people did in other ways in these backgrounds, like localization or integrability or.
So it's all in the case when there isn't all these checks.
Yeah.
There are situations when there is.
Yes. It
So
yes.
is there evidence that it holds beyond when there is no integrability?
No, I don't think so.
Well, in the case of ADS3, it works.
Yeah, in the case of AdS3 is again the really special case where you know exactly the worship theory and you can do the computation
Without using integrability.
without using integrability. But when you have like specific like flux and SNS, I think. But beyond that, yeah.
But it's not using integrability, but the background is still integrable or not.
Yeah, you can do it because in that case you don't have Ramon, then you have the worship,
Right.
which just
Yeah.
solid.
It's a very, very special case.
Yeah.
Apart from that, there is no result. That's why, like, the program was born as a way to guess the putative worship strings, but there is nothing to compare with. Okay, so one key point that I want to keep in mind is that single-valuedness, even if it seems just a mathematical fact and an evidence, still plays a fundamental role in the construction of AdS scattering amplitudes, and we definitely need to understand this better. But the big goal of the program would be to determine the amplitude to all orders in 1 over r, so define our answer, and also on the other side make connections to more direct worship computations. And it seemed that there is a way to study these two directions simultaneously, and it's the investigation of the energy limits. I don't want this to be the focus of the talk, but I will spend 2 minutes by just telling you the results.
Sorry, but coming back to this square structure, then kind of the expectation would be that somehow 4-point function of stress tensor determined by 4-point functions of like just some global currents. Is that-
Yes.
But,
No, sorry, what do you mean?
well, because analog of gluon scattering amplitude, that's some correlation of some currents, right?
In the double copy picture, you mean?
Yeah, I'm asking about the double copy.
Yeah, I will come to that because it's very not trivial,
Okay.
but
Okay.
it's
You
still
also
an open
keep changing
question.
dimension.
Yeah,
Will not be the same dimension.
yeah, yeah, it's much more complicated, but this is just going towards
Okay.
developing
Okay.
that.
Sorry.
Okay, before doing so, let me say one word about what we did before the last paper about double copy. The first point was the high energy limit. So you take S and T large, and in this setup, I think I'll go back to this later if there's time, but we predict that the amplitude in the energy limit is essentially the same result as in flat space times this exponential. This is an answer to all orders in S over R fixed. So it's a specific regime, and curvature corrections exponentiate. Essentially, in this regime, you can do the computation exactly, and just the first curvature corrections enter the game. And that's quite beautiful because then it imposes non-trivial constraints on the higher order corrections. Essentially, what I was saying.
So I'm
before.
confused. So the W6 is replaced by the square of W3 or so on and so forth?
Yes,
In what regime is this? I'm sorry.
S large and T large.
I see.
And the exponentiation happens when S over R is fixed. Yeah, you can do two computations, classical computation in AdS or the worksheet point of view because there is a saddle point approximation and they agree and they give us this exponentiation. Again, this is exactly the case for other backgrounds. So there is some universality in energy exactly as in flat space. But then you could do more. You can, yes,
That formula is something you computed independently of your answers with polylog.
sorry?
That formula you computed with an independent method compared to the other slide.
So like you can do this independently. The space-time computation is a classical scattering AdS, and this is the prediction, still polylogs. This is independent. But when you do the worksheet point of view, you start from our ansatz, which is this. And since these corrections are rational functions in S and T, they don't modify the location of the flat space saddle point in a 1 over R expansion.
Sure.
So you still have the flat space saddle point, and you evaluate this on the saddle point.
I'm just wondering if this W3 here and the W3
It's the
in the other
same.
slide. I know, but did you find them with independent methods or not?
No. So
Okay.
we do the computation in two different ways, and then we match them and we get this exponentiation. But one is relying on the ansatz and one is independent.
Okay, so they are independent.
Yes. These two, yes. But these no. Like this is by requiring that these two matches.
So it's a saddle point in what variable?
So it's S and T. S and T are large, right, in the high energy limit, and the saddle point is S over S plus T.
So this is fixed angle scattering.
Yes, fixed angle scattering.
It's not Reggio.
No, Reggio comes later, but definitely S over T is fixed. Yeah, exactly. After that, we investigated the Reggio limit, where T is large and S is finite. This is very schematic, but I can even precise later. What we found is even in this regime, to all orders, you can compute the amplitude as derivatives of the flat space Reggio limit. And this is a great result because even in flat space, the big achievement of Reggio theory is that you just need the leading trajectories and cubic couplings to get the answer, and this is the case also in AdS, modulo this differential operator which encapsulates the effect of the curvature of the background. And eventually this will hit the Reggio limit in flat space, producing logarithmic corrections in T. And this is interesting because you can translate this to the worksheet, and this teaches something. So this is just what I wrote before, but more explicitly. And since you know that you have derivatives of the flat space, you can ask yourself, but what is the right integrand that I have to put in the worksheet to reproduce the Reggio result? And that's just an expansion in single-valued logs, without knowing what was the full proposal. So it's a nice and expected, like, support evidence, I would say, for the full proposal. This manifests single-valueness around z equals 0. So there is a lot of input from these exact limits that led us to propose the mathematical structure. So I just wanted to remind that the high energy limits here are interpreted as a natural step toward an AdS worksheet theory, which is not known in general. And this enables us to probe the theory's mathematical structure across these different regimes. And eventually this culminated in the last work that we made together about the proposal of building blocks of string amplitudes in AdS and KLT relation in AdS at the level of these building blocks. So now we're going to be a bit more abstract, and this is more like a mathematical structure, but eventually we want to compute amplitude and still work in progress. So the basic object for closed and open strings in flat space are these kind of integrals, and they are known as the Euler and complex beta function. They are related by a single valued map, which is very similar to what I told you about the polylogs. So you can interpret the complex beta function, which is describing closed strings in flat space, as the single valued image of the Euler beta function, which is a linear map. But turns out that this has the same piece of information as the KLT relations, because if you develop this term by term, you eventually find that this is essentially the square of the beta modulo this kernel, which is exactly the kernel that I showed you before. So you can see this single valued map, which is linear, in terms of the quadratic KLT relations, that tells you that perturbative closed string 3 amplitudes can be written as bilinears of open string amplitudes. This is a key point. So in flat space, we have an explicit answer for the string amplitudes, this ratio of gamma functions of S and T, from the worksheet, and this is what allows us to study properties and relations. So we wanted to develop the same technology for AdS in order to gain some information about the worksheet itself. So how do we go to AdS? I tried to review how different techniques led to the computation of massless 3-level amplitudes for strings in AdS in different backgrounds. And across these backgrounds, the answer is always insertions of polylogs in the worksheet, putative worksheet. And we believe we are on the right track because the CFT data agree, as I was saying, with all the known determinations, but also the energy limits confirm somehow the full proposal, at least in some sectors. So our proposal is the following, easily guessable from what we discussed up to now. For the closed strings, we insert single-valued multipolylogs. For the open strings, we insert the multi-valued ones. And when the word is the empty word, you just recover flat space. Then you increase the weight, you will generate the AdS corrections.
So I'm confused about something.
Yes.
The single value polylogs are unique in the
Yes.
sense that you define them with a differential equation formula, a recurrence formula, and then that's it. But the other ones are not unique.
The multiple polylogs.
Yeah. So there is a sort of ambiguity in this prescription, right? Because the first line is clear what I have to do. In the second one, how are uniquely defined?
Well, even the single-valued ones are not uniquely defined if you like. Like, there are different ways to construct them. But we pick a basis where you construct them just as some linear combinations of multi-valued ones at Z and Z bar, and nothing else.
But in the other one, you have more ambiguities, right? Because
yes, but even there, like, there is a basis at each weight.
okay, the
you can
prescription
pick.
comes with some additional data or something like that, which base you pick up or something.
There's exactly the same number of
Yes.
single valued and non-single valued. For each word, there's one. And there's one to one correspond. For
Okay.
each straight L, you can build a curly L
Okay.
Yeah.
with the standard procedure.
It's a choice of basis, but it's the one from Francis Brown. And we follow his algorithm, but it's not unique, of course. And also, talking about non-uniqueness, you could have more terms, ambiguities that integrate to 0. That's taken into account, and you can fix those parameters in this limit as well. This is the easiest scenario, I would say.
Can I ask a question?
Yes.
So suppose I want to figure out what is the worksheet period. So I should think about this integrand as 4-point functions?
This is the building block. So like the
No, but
amplitude would be
yeah,
a
but
linear
if
combination.
I want to construct a worksheet
Yes.
theory, so should I think about this integrand as
Yes,
coming from
yes.
4-point functions?
Yeah.
What kind of 4-point functions? I mean, what kind of CFT produce? I mean, what kind of operator in the CFT would produce this kind of 4-point function?
Like, for example, the original work was in this 5 process phi, and it was a 20 prime operator in.
No, I
and it
mean
was
from the worksheet perspective.
from the worksheet.
What kind of vertex operators?
Well, that would be the graviton in this case, the original.
No, but
case,
that produce this kind of polylog dependence.
Oh yeah,
Like
that,
as a
that's-
toy model, right? It doesn't
Yeah,
have to
yeah,
be
yeah.
the.
No, I don't think that's a clear understanding of that. I think the most physical understanding would be if you expand the metric of AdS around flat space, the corrections can be seen as extra soft gravitons.
Yeah.
So
But
that's
it's,
the
this is a
best.
very primary correlator, right?
Not
This
that
polylog,
we know.
some kind of dressed
I mean, that would be the dream, to understand where the vertex, to spot the vertex operators in this picture. I don't think that's easy, the vertex operators are quite horrible.
But from this pure spinner approach, like
Yes.
Berkowitz and others, I think they were able to construct the vertex operators. Right?
Something, not the vertex operator exactly.
But do you get integrand of a similar form?
It's still not known. Like, people are working now on that. I think Fernando is working with other people from the pure spinner community,
Mhm.
but it's really open. Like,
But in a DS3 case where
Oh, yeah, and UES3.
I know that it's done. I don't know how to
Okay.
match the vertex operators just at the level of
That's good.
the results. But yeah, that's a good point. I should look at that. But yeah, it's still not known, right? So one thing that was known how to do was how to compute these integrals in a low energy expansion. They take this form, and this is actually back to Veneziano's paper, and these are polylog at 1, so again zeta values, but we want actually analytic expressions in SNT, so finite SNT. And up to weight 4, we show in the paper that the J integrals can be computed analytically, and we classify them in terms of some generalized hypergeometric functions. Actually, we find the answer for any weight for those of you who are working with special functions that are called Amato-Gelfand hypergeometric functions. And that's it. That's the best we can do. Then for closed strings, it's much harder. And you still have a low energy expansion, so these are single valued multiple zeta values. And in this sense, the closed string amplitude building blocks are the single valued version of the open string building blocks. Again, we managed to find some explicit results up to weight 4 by direct integration and combinations of some nice properties of hypergeometrics. But what we want is something way more general, something that works at any weight. And the idea was to generalize the KLT construction to the insertions of polylogs. Because even if I didn't tell you, the original KLT paper was just a manipulation of contour integrals. And this science comes from the monodromies of these integrals. So actually, back to this paper, which was before our work, in an appendix, they show Fernando found a way to extend the KLT prescription to the insertion of a single valued function. And if you care about the details, that's how it's done. So, but the lesson to learn is that if you insert single value multipolylogs here, which is what we want to do, you can always factorize the integrals into two one-dimensional integrals involving multiple polylogs. It's non-trivial, we have to keep track of discontinuities, but that's how it works. And okay, this may be completely like obscure, but I just wanted to show that you can do this prescription explicitly. For example, for this integral at weight 3, it's the specific result, but you only care about the fact that you can compute the result as bilinears of 1DJ integrals. And the flat space KLT kernel keeps popping out, of course, by construction. So motivated by the KLT relations in flat space, the constructions of single-valued polylogs from the multivalued ones, and these explicit results that we could get up to weight 4, we propose a relation between the building blocks of open and closed string amplitudes in AdS, which is what goes towards this development of double copy in AdS. So let me stop for a minute. I just wanted to tell you what was known before our work, and this is actually at the level of the amplitudes. So double copy works quite well for 3-point amplitudes in AdS, and this goes back to these works. And color kinematics duality, which is another nice properties of amplitudes that I didn't talk about, holds also for 4- and 5-point functions in AdS, while higher points is a bit non-trivial. But a key point is that in flat space, color kinematics duality is implied double copy, while this is not the case in AdS, or at least not easily, because people managed to get sensitive amplitudes by doing so. And the first example where a double copy worked for 4 points was proposed by Shinan in 2021, but this is for the reduced amplitude, which is what you get after applying some superconformal word identity, essentially. There has been a lot of progress also in twistor theory, classical double copy, and progress in de Sitter, but the key point is that there is no systematic formulation of double copy in any curved space-time, and no definite prescription for building blocks for gravitational amplitudes. So we really need to understand how much of the flat space structure persists when you go to AdS. So we go back to our friends, and we propose a way to relate them, inspired by this KLT prescription. So the generalization of the Euler and complex beta function are related again by a single valued map. This is by construction, but we learned that this is essentially, mathematically speaking, the same thing as the KLT. So we expect that a kernel exists that allow us to recycle the results for J, which are completely classified, and allow us to compute the Young integrals. Yes?
Is the first identity obvious?
The first identity this?
Yeah.
Yeah, because to be precise, a single valued map works
It's always
order
for the
by
integral.
order in f prime to 0. So
Oh.
you do f prime to 0, you have a bunch of zeta values, and order by order you can substitute the zeta with the single value.
Mhm.
So the even one you kill them, the odd one you put the 2.
Yeah, but is it obvious that that equality holds?
Yeah, because I mean this integral, when you integrate each polylog on the Riemann sphere, you always get the same numbers. Exactly.
And isn't that, like, it's a lot simpler than the second equality that you had?
No, because this works just in the alpha prime to 0 limit. Even mathematicians, when they want to do this like globally, they need to go through a quadratic procedure, which is the same at the end of the day, and it is much easier, but this strictly speaking is at the level of numbers and functions. Okay, so this is technical, but for people who like maths, this is the way we found this kernel. So what we use is a language of generating functions. The usual story of encoding an infinite sequence into a single function. So you have polylogs, right? I told you that you have weight 0, 1, 2, and so on, but you can package them all together in a generating function of polylogs, and then essentially you integrate the generating function and get the generating function of these building blocks. So we wanted to have a result to all orders, so we work with generating functions, and that's the proposal. The details I'm happy to discuss for those of you who care. And this kernel, of course, needs to start from the flat space answer, and the corrections needs to be only trigonometric functions in SMT, as in flat space. And remarkably, we compute the kernel with some manipulations of integrals, and we find that the kernel takes a remarkably simple form, which is the following. It is really remarkable because it works at all weights for any polylog. These M0 and M1 are monodromy matrices that we expect to happen, of course, and they essentially govern the discontinuities of multiple polylogs as you cross the real line. They have been computed by Francis Brown, so even more explicitly, you can just plug them back here and do the computation. And it turns out to be quite beautiful, I have to say. So this is the inverse of the kernel in flat space. It's just the inverse of the sine over sine that I showed you before. And this is the way to generalize it to AdS. So the shift by S is from these E0 and E1 that are two variables associated to 0 and 1, the letters of the polylogs. And the shift of T is a bit non-trivial. You have this multiplication by this function of E0 and 1, which is a generating function of zeta values that still you expect to be there. So one thing that I didn't say is that these E0 and E1 are non-commutative variables that you can show they have to be non-commutative because of the algebra of polylogs. So it is very non-trivial that such a structure exists, because as you move slightly in some factor, everything gets messed up.
So again, what are M0 and M1?
Are monodromy matrices of these polylogs. So they encapsulate all the discontinuities as you cross the real line for any weight.
So this kernel acts on
Like this. You have the generating function of multi-valued polylogs with some adjustments that is completely natural. It mirrors how you construct single-valued polylogs from multi-valued polylogs.
So how big are these? Because these are vectors, right? It's J.
Yes, this J is like for example this, right? A generating function. So it's an infinite series. To all order, you can do the computation for all the infinite weight.
Yeah. No, but you say that these M are matrices, right? So what's
M0
the
and
order?
1, for example, M0 is e to the 2 pi I s E0.
So, but what's the order of these matrices? I mean, they are n by n.
Right. There are functions of E0 and E1 in
Yes.
this language,
Just
right?
keeping track of the basis elements through coefficients of E0 and E1. I mean, these are algebra generators.
Yeah, algebra generators.
So because it's generating functions of E0 and E1.
Yeah.
And so multiplying them by M0, which
Yeah.
is also a function of E0 and E1, corresponds to reshuffling
You
of
just need to-
coefficients, right?
yeah.
And corresponding to monotony. That's,
Yeah, yeah.
that's
That's okay, but then, I mean, how much of this, if we want to...
If you want to read out like the relation between the function, you expand in the same basis of E0, E1, and
Yeah.
look up the coefficients.
You can do this order by order, like you compute the j integrals up to some weight, and then you compute the kernel. But what we managed to do is to compute the kernel to all orders. If you can look at the paper, but essentially you plug this into the holomorphic factorization form, and it comes out quite naturally that this is the answer. And once you plug the results, that's the answer to all orders.
This M0 and M1, is there some closed
Yeah.
expression for them as functions?
Yes, M0 is e to the 2 pi I as
okay, that's
E0, and same with T, but with this multiplication of Z.
Because that's precisely the shift, right? The shift
Yes,
is-
okay.
it maps precisely
Ah,
this
that's
shift.
okay.
Yeah.
Yeah.
Okay.
Yeah, I should have written them.
Is there like a physical meaning you can attach to the amplitudes with this E0, E1 as well? Some kind of polarizations?
Oh. That I don't know. We didn't think about that. Could be. For us, it's just a language.
Yeah,
right?
I see from the formula.
Yeah, but it could be that there is more. I don't know. I would say, I don't know. This works at the level of the building blocks. Works nicely, and it's an amazing result because you can compute, in principle, each order AdS corrections now. Which is, of course, is non-trivial, it's complicated, but the answer is explicit.
And this algebra E0, E1, just free algebra? There's no...
Yes. Yeah, it's completely studied by mathematicians, so once they write papers, we can make progress. Okay, with that, I'll give you some key takeaways. This was an example on how to make progress about string aptitudes in AdS from alternative tools, such as AdS-CFT, number theory, integrability, and exact limits. And we can really learn a lot from looking at flat space and high energy. Also, people computed the same answer in other backgrounds, and it turns out that there is some universality of structure that still needs to be investigated. But this led us to propose a unifying mathematical structure. So the first step was to propose these building blocks at tree level, and this allows us to compute in a closed form AdS corrections. Eventually, this culminated in the proposal of stringy KFT relations that, even just at the level of computations, is really strong because you cannot do, you can explore the worksheet, I would say, and then go back to its physical meaning. But of course, a lot remains to be done. And I want to stress one last time that progress in flat space is based on explicit results via the worksheet theory. So we need to do explicit results as a first step. But also there is a whole story that I didn't say about the inverse of the kernel. Because if you look at this, the nice expression is just for the inverse of the kernel. The kernel itself is way more complicated. But there is a whole story, very similar story in flat space, where the inverse of the kernel is special, and actually it can be interpreted as physical amplitudes in the adjoint scalar theory. We don't know how to extend this story in AdS, it's an open problem, but we expect to find some geometric interpretation there as well. And of course, the question now would be how to find the KLT between amplitudes, specific amplitudes in specific theories. It is very non-trivial because it is for the building blocks, but then they are, of course, in a linear combination, the quadratic procedure is very non-trivial. And the ultimate question would be to find the direct string theory computation, like with vertex operators and so on, that would map to us. But at the moment, people are still working on this. And with this, I would thank you for your attention.
So the flat space double copy, it relates amplitudes in different series.
Yes.
So here it relates amplitude, the correlators of different operators in the same series, or how I'm supposed to think about it?
We don't know. This is the honest answer. People have tried with like AdS 5 cross S5 and AdS 5 cross S3. So like these 4-point case, Shinanzu 2021. That's the only paper that we have for 4-point functions, but it works for reduced amplitude. It's very specific. You need to do some adjustments by hand. That's why we think we need to find a more natural language, which seems to be this number theory.
But
Yeah.
if I understand correctly, what Sergey wants to ask is that can you phrase this double copy relation in the CFT language, like in
Right,
the
yeah, exactly.
in the inverse Suprameos?
Yeah.
Basically,
What
so
is
the
this
lake
pers-
can on a CFT
Like, is
to
there
some
a-
to some non
Yeah.
like CFT with infinite central charge, which
Yeah.
doesn't have T mu, but
Yeah.
have some
Yeah.
just currents, right? And
Yeah.
so-
It's relating the inverse Suprameos stress tensor 4-point function with some other observable in another CFT.
I would say so. Even this Veneziano thing comes from ideas 5 crosses phi, like mod Z2. Like you need to change the background. I would say you. I think people change the background when they do these things.
Mhm.
But I don't think there's any result in the same spectrum, the same theory.
Yeah.
I have to check.
Maybe it's related to these questions that Gaston asked also before, maybe. But I want to see the consistency of holography with squaring. Holography tells you that one gauge theory equals a gravitational background.
Yeah.
Now here you can have the idea that you square and get a gravitational
Mhm.
background. So does it mean that a squared gauge theory is like a gauge theory?
Well, it's a bit different because in holography you have strong coupling, weak coupling. While here you're doing both weak coupling. Like double copy is building blocks for weakly coupled graviton gauge.
In principle, it should be true for any coupling. So
Yeah, but still weak coupling equal weak coupling, strong coupling equals strong coupling, right? It's a totally.
No, but to me, what worries is square of a theory is
But
not.
stripped
is
of
it-
the color factors, though. Stripped
Yes.
of the color factors. So it's really, I think for me, I don't see any obvious relation between the two facts.
No, but is there a claim that the square of a gauge theory equals a gauge theory?
A square gauge theory in which you take out the color factors, so the factors of n,
Yeah.
like in SUN or n square, and then you multiply by this kernel. So yeah, I mean there is a correspondence, but it's not one-to-one.
No. And you get gravity with stripped off coupling as well.
Now, there was also instead a perturbative relation between open string diagrams and closed string diagram, and it's in the relation used, for instance, years ago by Maldacena of computing the scattering of what was it, of closed gravitons using open strings or vice versa. I mean, using the open-closed string duality. So I don't know if there is any relation between this double copy and open-closed.
We haven't investigated that yet.
At one point, you had a picture. I think you quoted the paper from Izura.
From
Can you
Sebastian.
explain a little bit? Because that's somehow going towards proving
Yeah.
this double
This?
copy. Yeah.
So that's like a flat space. This is the closed string amplitude
Yeah.
with the warsheet, and this is the open string, and that's the kernel. Like geometrically, you can think of it as the gluing of. But you sum over all the possible way to glue them to the kernel. And the geometric interpretation is very mathematical. It's this intersection numbers theory, and it tells you that. I mean, that's pretty natural the way that it emerges, but I'm not familiar with the language.
But would you say this is proving that this double copy relation at the level of the string amplitudes, tree level amplitudes?
I wouldn't say it's proving. I would say it's a picture for the warsheet for strings.
Towards the end, though, you mentioned that there's a relation between this inverse kernel and the scattering amplitude in a B-adjoint scalar theory.
Yes.
So, two questions. One, how is that related to this? And the second question is, I can see, like the B-adjoint scalar that I'm used to is just a cubic theory
Yes.
for scalars, so that would be alpha prime equals 0. What is the theory at each order?
Yeah, it's the stringy completion that's been computed by Misera as well
Okay.
in 2016 or 17.
And is it related to this?
Yes.
Okay.
So it's the inverse of this kernel is is a matrix with where the entries are the matrices, the amplitudes of this stringy completion of the adjoint scalar theories.
How does it look like roughly?
Like trigonometric functions in SNT.
No, the Lagrangian of this theory.
I don't think there is a Lagrangian.
Well,
So you have
order by
infinite
order alpha
terms.
prime.
Yes, I mean you have alpha prime cubed and alpha prime fifth corrections. I don't
Yeah, but-
remember exactly
okay.
that. But because it doesn't care about that, it does some diagrammatic deduction. So like in the Biot-joint scalar theory, you have a graphical interpretation. You can do computations exactly, and then essentially it finds new Feynman rules for the stringy theory, bypassing the need of writing down the Lagrangians.
It just sounds like there's a unique
There is no
stringy
unique-
completion of
No,
phi
okay.
cube theory.
No, there is not. It's like the only known stringy completion. So
Well, but it's preferred. Not
preferred, yes. I don't know. Yeah, it's preferred.
This is related anyway to like this fishnet type models.
No, I don't think so. Or maybe yes, but not that I'm
With also
aware
the
of.
pure. I think that's also a phi cube theory, right?
Yes, but
Yeah.
this paper it's very diagrammatic.
You can have cubic coordinates. It depends on the dimension.
Yeah. I'm talking about fishnet from the expression models.
Isn't that cool?
I forgot.
Yeah, I think you have this like diagrams are
Yeah.
lattices, so you have 14 interactions.
Yeah, that's how I put it.
Okay. Any other questions?
So could you comment a bit about what it looks like in de Sitter space?
In
is
the
that-
sitter,
Yeah.
I'm trying to.
Is it some double analytic thing, or is it,
I honestly,
you
I
said
don't
there was
know.
some progress in de Sitter last
There
time.
is progress about the double copy. I don't know. I mean, I think they study cosmological correlators and they go back to the sitter, but honestly, it's not my area at all.
That's it. Maria again.